We must try to systematize the phenomena we see around and try to describe them in a unique way in a complete order. Everything must be the result of the minimum number of hypotheses, parameters, constants of interaction and other quantities which are introduced into the theory by hands. All the rest must be the result of the adequate mathematics, which is able to describe dynamics of any system in any conditions. There is a known fact of the incomprehensible efficiency of mathematics in natural sciences. It was observed by Evgeny Wigner, and until now there is no answer to this question. Physics uses it, its language is mathematics, but why it is so effective nobody knows. The mathematics is really fantastically effective in understanding of nature. Let us have a look at Einstein's general relativity. It can be formulated as follows. It is a certain theory comprising self-sufficient geometry. Why? Because there is the pseudo-Riemannian geometry, where it is possible to produce various geometrical constructions, measurements, etc. Knowing such geometry, it is possible to find the equations of motion for the material objects or for the test particles. Moreover, knowing such geometry, we can write the equations of field for the metric sensor. That is, if we know pseudo-Riemannian geometry, we needn't know anything else, we already have everything. The equations of motion for particles, the equation of fields, the gravitational field and the geometry as it is. It turns out that the physical world corresponds not to a single geometry, but to a certain class of geometries. Depending on what problems we solve, we could probably choose various geometries. Geometry we are used to, in which we used to live, is very close to Minkowski space or to Minkowski geometry. But it is not obvious that at large distances, such as distance to quasars or distances in a microcosm, the same Minkowski geometry works. It's not a fact. First of all, let's understand what geometry is. In geometry, the spatial relations between objects are defined. And the first question is how to calculate the distance between 2 points. In Euclidean geometry, which we study at school, this question is solved by means of Pythagorean theorem, when the hypotenuse square is equal to the sum of square of legs. But imagine another situation. For example, the distance is a fourth root of the sum of the fourth powers of the basic distances. Can nature be arranged in such a way? It can. Nothing forbids it. Already Riemann paid attention to this in his well-known lecture on the hypothesis lying in the basis of geometry. And systematically it was studied by Finsler, who was the professional mathematician. The correlation that defines the distances between pairs of points gives the so-called metric of the space. The quadric metric fits the Pythagorean theorem. This is the most habitual, but as we see, not the unique version. Though Riemann has specified the basic possibility to replace the second power in the expression for metric for the third and fourth powers, he was the first to reject the idea because of the complexity one has to deal with working with such geometry. The quadric matrix is also used in the relativity theory, though even at the first glance it would be more beautiful and more logical to use the metric with the fourth power to describe the four-dimensional space-time in which we live. The metrics that could be interesting to physicists unfortunately are few in number, although their total number is infinite. First of all, those metric functions could be of interest that works in 4 dimensions, because these 4 dimensions are what we can perceive and measure. Nobody has ever observed a 5th dimension. But if for the description of physical phenomena it is possible to use various geometries and various metrics, how to choose the most suitable one? But maybe we should go on even deeper. And then, beginning with Hamilton, the remarkable idea, which goes back to Pythagoras, has been put forward. At the heart of our world there is a number. At first, numbers are perceived as purely algebraic thing. Here is arithmetic, there is algebra. No link to the description of the world or to the universe design can be seen. Pythagoras dreamed to describe liking, friendship and antipathy by means of integers, but it was a naive idea. There is no obvious link between arithmetic, algebra and universe description. Euler was the first to outline this link when it became clear that complex numbers describe a plane. Complex numbers describe the geometry of a plane, that is already geometry, it is already closer to the world which we see. And then Hamilton posed a question: which numbers could describe the three-dimensional world? He discovered hypercomplex numbers, quaternions. And it was after Hamilton that the thought appeared: in the heart of the world description there is algebra. So we expand the notion of a complex number to hypercomplex number, and the hypercomplex number is a certain code of nature which explains its structure. That is, our world has some structure that is not amorphous, and the essence of the structure is expressed by hypercomplex numbers, so to say, according to Hamiltonian's dream. If we manage to understand the code of nature, understand that hypercomplex number which underlies the world, we will at once realize why our world is such and not the other. Because algebra is a very strict thing. If we can say that the given number system is better than all the others, that it has certain remarkable properties, then we will tell that geometry follows from this algebra. And geometry, as it is already known to modern physics, is the source of physics, and we automatically understand how the world is arranged. This was that, a bit crazy, Hamiltonian's idea. Go beyond the limits of such an all-sufficient object as complex numbers. Namely, invent hypercomplex numbers, but not to solve the algebraic questions, but to solve the geometric questions. To understand the geometry of our world with the help of hypercomplex numbers. And here we have a crossroads, because after complex numbers you can go in various directions. There are several hypercomplex systems, and not so few. Some of them have better properties, others have worse. And one could act as Hamiltonian did. Use quaternions, biquaternions, octaves, but it is possible to invent other hypercomplex numbers and try to find the code of the universe, the structure of nature in them. Indeed, even in 4 dimensions there is a lot of hypercomplex numbers. We investigate, as a matter of fact, only those hypercomplex numbers which possess the commutative associative multiplication, or polynumbers as we call them briefly. In frames of this approach, the 2-dimensional space is based on double numbers, the 3-dimensional space on triple numbers, the 4-dimensional space on quadrunumbers, and so on. The algebras of such numbers appears to be simple sums of common algebras of real numbers, and the corresponding polynumbers are simpler than many other hypercomplex numbers. Usually, algebras are determined by their operations of multiplication. For example, the quaternions have beautiful and laconic basic multiplication table. And quadrunumbers have even simpler multiplication table. The minus signs disappear since the quadrunumbers have hyperbolic imaginary units. As a result, the product of quadrunumbers possesses the same properties as the product of usual numbers. Besides, there is a remarkable possibility to pass from the usual orthonormal basis to the isotropic basis, in which the multiplication table becomes absolutely elementary. Extremely simple in this basis is also the expression for the quadranumber modulus, which produces already different metric. Not Euclidean one, as quaternions do, but Finslerian, Barold-Moore metric. Now we have got not the second-order form usual to physicists, but the fourth-order one. So, simple at first glance, this algebra leads to an interesting, but not so simple geometry. the geometry in which the distances between points are defined by the expression of the fourth order instead of usual Pythagorean theorem. But what to do then? Pythagorean theorem is supported by all our practical experience. It turns out that this problem is quite solvable. All visible contradictions will cancel out if at scales less than the size of the visible universe, the intervals between points in the four-dimensional Finsler space with the Burwald-Moore matrix are almost equal to corresponding intervals in the pseudo-Euclidean space with the usual quadratic metric. Then Pythagorean theorem with its sum of squares of the triangle legs appears to be a limit case for the expression of the fourth order in the definition of distances in Finsler space. The concrete four-dimensional metric is chosen because in some range of the geometrical parameters it has the properties indistinguishable from Galilean geometry, the geometry of classical mechanics. The well-known Minkowski metric also has such properties. In our opinion, in the pre-relativistic range of velocities, our form is not worse than Minkowski metric. Whether it is better in the relativistic range and in wider range of various parameters is an open question. I think the near future will show which metric function better corresponds to observations and experiments. Let us have a look at similarities and distinctions between spaces with two so different metrics, with the help of one of those basic objects of the relativity theory, with the help of a light cone. This is a region in which the light beams propagate, passing through the fixed point. In case of two-dimensional spaces, there is no difference between light cones in pseudo-Euclidean space and double numbers space. For three-dimensional pseudo-Euclidean space, this region looks like two cones connected by their tops. The name light cone originates from here. For Finsler triple number spaces, the analog of a light cone gives two trihedral pyramids also connected by their tops. And for the quadrinumbers, four-dimensional space, there are tetrahedral pyramids. At first glance, there is too big difference between a cone and a pyramid to speak about any similarity. However, in this case, the characteristic cut form of a pyramid is related to the light velocity, and in practice we mainly deal with the pre-relativistic range of velocities. In this case, the distinction between two spaces are not so great, both in qualitative and in quantitative sense. Let us take two light cones of Minkowski space and cross the cone of the future with the cone of the past. We see the figure resembling children top, and the cross-section of the cones is a flat circumference. This geometrical procedure has the concrete physical sense. Let us assume that at some -t moment in time, the motionless observer sends signals with various velocities at every direction, and they return to him at the moment of time plus t. Then his two-dimensional physical space is a plane, orthogonal to the time axis. And the concentric circles are the points of physical space, equidistant from the observer from his point of view. Similar construction can be obtained for Finsler three-dimensional spacetime. Crossing a pyramid of the future with a pyramid of the past, we get a three-dimensional cube instead of a top. And the crossing line of the light pyramids appears to be not a flat circle, but a closed, three-dimensional broken line. Now let the motionless observer, living in such a world, again send signals with various velocities at every direction at some -t moment in time, and they return to him at the moment of time plus t. If we look at this from the outside, we will see that the physical world of this Finsler space inhabitant looks like a soap film spanned on a broken hexahedron. However, the geometry of the two-dimensional physical space in the center of a soap film practically coincides with the geometry of a central region for the case of pseudo-Euclidean space. It means the existence of the limiting transition from one geometry to another, and a similarity of both spaces on small scales and for small velocities. But if at all this is so close, why is it necessary to change anything? The thing is that Finsler spaces with Berwald-Moore metric have a variety of favorable advantages. The geometry connected with the Pauli numbers is surprising and interesting because it possesses an infinite conformal group of symmetry, that is, an infinite set of conformal transformations. Any four-dimensional space with a quadric metric possesses only a finite group. In three-dimensional Euclidean space and in four-dimensional Minkowski space, there is no such surprising variety. That is why we are interested in these antagonists. Particularly, the four-dimensional Berwald-Moore space, as well as a complex plane and pseudo-Euclidean plane, possesses an infinite conformal group. The thing is that a very important role in the perception of our world and in classification of our knowledge is played by symmetry, by the concept of symmetry of object and by the symmetry of nature. It is impossible to understand physics without symmetries. Besides, there is no other theorem from which it follows that all the continuous symmetries of the Euler-Lagrange equation are necessarily connected with the conservation laws for the physical system described by this equation. That is, the symmetry and conservation laws are just different images of one and the same. If you wish to deal with physics and conservation laws, please be so kind to find the symmetries that underline this physics. Another potential advantage of Finsler geometry is that there is no need for a considerable number of dimensions to solve one of the most actual problems in physics: unification of all known interactions. Unlike the majority of modern geometrical models that use multidimensional spaces with 10, 11 and even more dimensions, we focus on a four-dimensional Finsler spaces and on four-dimensional space with Berwald-Moore metric. Such choice corresponds to the fact that from the topological point of view, the four-dimensional space is the most diversified in its displays. It is the most difficult and accordingly it is the most substantial. This idea is in air for a long time. But if we start with usual Riemannian geometry, four dimensions are not enough. It is impossible even to unite the gravitation and electromagnetism there. And with Finsler metrics, it is possible to unite the gravitation and electromagnetism in four dimensions. There remain even additional degrees of freedom, which allow us to hope to describe also quantum effects. Because of its big drawback, that is the presence of too many free parameters able to acquire this or that physical meaning, Finsler geometry has its main advantage: the possibility to use this approach to obtain uniform design, connecting both gravitational and electromagnetic interaction. By means of Finsler geometry concepts, the gravitation and electromagnetism unite. No problem. And they unite rather naturally. Moreover, the principles of self-sufficiently of Finsler geometry gives the equation of field for gravitation and for other fields, and then the tensors of energy and momentum. There is no such problem that arises in the general relativity theory. One of the basic objects for Riemannian spaces is the metric tensor, which has a form of square metrics and which is the base for the construction of general relativity theory. In three-dimensional pseudo-Euclidean space, metric tensor has 9 components, only 6 of which are independent. In three-dimensional Finsler space, the analogous metric tensor becomes not a flat two-dimensional matrix, but a three-dimensional object. The number of its components becomes equal to 27, 10 of which are independent. For four-dimensional Riemann spaces, the metric tensor is flat and has only 10 independent components. These are not enough, and this leads to the multidimensional space theories. And for Finsler four-dimensional space, the metric tensor becomes a four-dimensional object with 35 independent components. quite sufficient number of degrees of freedom to contain potential not only of gravitational field, but also of the other fundamental interactions. Nowadays, the theory of great unification of all the four interactions is at the very beginning, and it is quite possible that the connections with the Finsler geometry have prospects. The important question that underlies modern crisis is an attempt to unite the quantum mechanics and the gravitation theory. These two disciplines are very hard to incorporate. The gravitation theory is actually a geometrical one. It is the theory of the scene on which the events take place. The quantum mechanics describes the interaction of the subject and the object. It is the theory connected with the observer, and it answers the question what can the observer know, to what extent he influences the events. And it is clear that the theory which tries to unite, so to say, such a subjective issue as quantum mechanics and such an objective issue as gravitational theory is a theory which deals with the basic question of philosophy concerning mutual relation between object and subject. It is clear that such unification won't be an easy job. And it is natural to find ourselves in an ideological crisis in which front decisions are impossible. An important point which demands a detailed mathematical study is the possibility to describe quantum effects with the help of Finsler geometry. The problem of quantization and the general relativity theory stands at the first place. This is why there is no complete theory of quantum gravitation now, and it is not clear when it's going to appear. Probably the approach connected with the change of the space metric will allow us to quantize this space, that is, to quantize the metric. And also define some equations that will describe most adequately the quantum features of gravitation. What do we need to find this unification for? So to say, the question has ripened. The development of quantum mechanics, the development of the field theory, give the description of all interaction but the gravitation. Gravitation is the next. This unification seems such a little question, one could actually think, why? But actually, it's a very deep point, because as soon as you add the fourth interaction, gravitation, you automatically get all the theory of the universe evolution, from beginning to end. You get what is called quantum cosmology. That is, you already describe the world in its deepest lines. You actually deal with the question of how the world is actually arranged. It is a fundamental question. It really is. Finsler geometry with Berwald-Moore metrics has another advantage, which is a consecutive of the link between this geometry and commutative associative hypernumbers and with the infinite groups of continuous conformal transformations. It is the possibility to construct not only two-dimensional, but also multidimensional algebraic fractals. The fractals on complex numbers are widely known. There exists a developed field which is already branched. There exist computer technologies that are not complicated. They are used in some technical applications and even in art. 3D graphics that use fractal images to present various surfaces and fractal landscapes. In fractal art, people try to make pictures by means of the computer. Nobody managed to construct 3- and 4-dimensional algebraic fractals within the limits of quadratic geometry. The objects that are built are geometrical fractals. There is no that infinite conformal group which twists and makes so surprisingly beautiful and interesting Julia and Mandelbrot sets in the two-dimensional case. The general purpose is to construct fractals on polynumbers like H4 or H3. And what we do now is trying to build fractals on double numbers. We managed to construct the fractal analogues of Mandelbrot set. The set whose property is that any part of it reproduces the initial set. We finally obtained Mandelbrot set, and when you take each single slice, zoom it, and see this fractal coming out, it grasps one's breath. In the same way, for the analogues of Julia set, we managed to obtain fractal objects possessing the same property of similarity of the whole and its part. Thus, we managed to show that on a double variable plane it is possible to obtain fractals. This result is a pioneer one now, nobody has done it yet. And in Finsler geometry, the infinite conformal group exists both in 3 and in 4 dimensions. An idea appears to construct fractals in 3 and 4 dimensions. If we do it in 4 dimensions, one of them should be treated as time coordinate, and then the other 3 will give the usual 3-dimensional space from the point of view of the observer. The first steps in these directions are made. Of course, there is still much to do and investigate, but already now it is clear that the obtained 3-dimensional and actually 4-dimensional pictures are interesting. And at the heart of this interest are those continuous symmetries that operate a conformal group. There is a hope that in such 4-dimensional, or better say 3+1-dimensional fractal patterns, the patterns of the physical world would reveal themselves. And then it will be possible to replace the study of physical regularities and of the physical object interaction, well, of course only partly, not 100%, by the mathematical experiment with fractals. It is an enormous economy. These are the enormous new possibilities. And if it turns out that the continuous symmetry of fractals and the continuous symmetry which we observe in the form of conservation laws in the physical world around is almost the same, then it will be a very small difference or no difference at all what to study, the mathematical world of fractals or the physical world of real objects. A certain astronomical object, red square galaxy, looks as if it was taken out from our constructions. Amazing similarity to some of the fractals that we obtained. One could also recollect the interference phenomenon. The pictures for very many sets turn out to be very similar to some physical cases of the interference of waves. In this sense, it could be possible to speak of some direct correspondence. The prospects are tempting. But working out the uniform theory, covering all the sides of our universe, demands big and long efforts. Is it possible to estimate the efficiency of the approach chosen by scientists to test the correctness of their way? Such a possibility exists. It is connected again with an idea of the anisotropic properties of our space. Finsler geometry, when the metric form has an order higher than 2, and the geometry is not quadratic, always leads to an isotropic space of the observer. That is, the anisotropy of space and Finsler geometry are just twins. Of course, it is possible to investigate anisotropy of the Riemannian geometry too, but there it is introduced by hints. In Finsler's geometry we postulate the metric form, and the anisotropy turns out to be a consequence of this first and the only postulate. If we see these manifestations on experiment, in observations, a certain number of multipoles and a certain number of interesting anisotropic features, we can tell that we move in the correct direction, and this geometry corresponds to the real world. When we start with Riemannian geometry, we have to make observations first, and then find the correction factors sufficing the observations and describe what we see. These are different physical approaches. One from theory to observations, and the other from observations to the correction factors in the theory. If we have investigated theoretically this or that Finsler space, we can predict the physical properties that will surround the observer living in such Finsler space. Let us come back to our observer living in three-dimensional Finsler spacetime. We see that his physical world presents a broken hexahedron. We see it from the outside, but the inhabitant of this space doesn't see any hexahedron, since the light beams sent by him at the moment of time minus t at every direction, and having reflected from other borders of his world, return to him at the moment of time plus t, also from every direction. He will see an unusual spherical sky. However, on this sky there will be 6 special points, whose properties are different from those of other points. As a result, the inhabitant of the three-dimensional Finsler spacetime will see his two-dimensional physical world as anisotropic, and the anisotropy of this physical space will be characterized by 6 specified directions. However, we live not in three-dimensional but in four-dimensional spacetime, and if it is really a Finsler one, how many specified directions will there be? To answer this, turn back again to our light cones and look at them with regard to the geometrical figures obtained. In two-dimensional spacetime, the cross-section of the light cone of the past and the light cone of the future gives a square. The square is the same as a cube, only a two-dimensional one. Then the observer at the moment of time plus t sits, so to say, on the top of a two-dimensional cube, that is a square, and looks along its main diagonal, that is along the axis of a light cone. And we get 2 points on the border of its one-dimensional space. Now pass to the three-dimensional Finsler spacetime and again cross its light pyramids of the past and of the future. We obtain a usual three-dimensional cube with an observer who again sits on its upper vertex and looks along its main diagonal. Physically, he will see the spherical world, since he can perceive signals whose propagation velocities do not exceed the velocity of light. However, on the border of the spherical world, there will be 6 special points which correspond to the vortices of a hexahedron. The hexahedron, which our observer would see if he looked at his world, not physically but geometrically. Then, by analogy, and in strict correspondence with mathematics, we have to sit on the upper vertex of the four-dimensional hypercube and to look along its main diagonal. For want of habit, many of us will have problems even to imagine a four-dimensional hypercube, to say nothing of looking from it in a certain direction. But the mathematicians did that for us long ago. Here is how the four-dimensional hypercube will look like if we take it in hands and fiddle with it. And sitting on the top of a hypercube and looking along its main axis, we will see a rhombic dodecahedron, a body with 14 vortices and 12 faces. It means that the three-dimensional physical space should have anisotropy, which on the scales comparable with the size of the universe is characterized by 14 special directions and by 12 special zones in the sky. This anisotropy should have global character. This is the prediction of Finsler geometry with Berwald-Moore metric built on Pauli numbers. And what do we have in reality? We can predict 2 phenomena that could be found in astrophysical observations. These phenomena would either confirm our ideas dealing with Finsler geometry with the Berwald-Moore metrics, or force us to reject them, to reject this activity. The first effect is anisotropy of Hubble parameters distribution on the sky. The investigations show the presence of a quadrupole anisotropy, but if we accept the idea of space with Berwald-Moore metrics, then the more accurate measurements must give also an octupole anisotropy. It means that in case of Berwald-Moore geometry, the astronomer will observe not 4 extrema on the sky, but 4 plus 8 equaling 12 extrema. 6 of them will be maxima, 6 will be minima. This is the prediction which we speak about. Besides, this anisotropy will be seen not only in the near zone at distances of order of 100 megaparsec, but also at distances of order of gigaparsec and further. Moreover, the further is an object, the larger is the difference between minima and maxima, and they won't level as it follows from modern isotropic models. Really, if due to more accurate measurements we add an octupole to the already found quadrupole, which has 2 areas of minimal values and 2 areas of maximal values of Hubble parameter, we will have 4 extra zones of minimum and 4 extra zones of maximum, and we will get 12 specified areas on the sky that exactly correspond to 12 faces of the rhombic dodecahedron. But the quadrupole in the distribution of Hubble parameter practically coincides with another quadrupole, which is found in the distribution of tangent velocities of quasars. The quasars seem to exit some points of the sky and be directed towards the others. Up to now, nobody has counted the exact number of such special points, and nobody can find any physical reason for such strange and ordered behavior of quasars. If more accurate measurements show that there are exactly 14 such points, and they correspond to the ideas of the rhombic dodecahedron, it will be in full coincidence with the predictions of Finsler geometry of our space-time. However, the measurement of tangent velocities of quasars give another result, which contradicts the relativity theory. Some quasars appear to move faster than light. Long ago, the following example was mentioned. The sunlight spot from a mirror can in principle move on a wall faster than light. But this is not the motion of a real material body, it is the trace of a light ray. Perhaps what we see, and which seems to us to be moving faster than light, is also some optical effect. In case of Finsler geometry of our space, it really turns out to be a specific optical effect, an illusion. The similar illusion is the ordered motion of quasars. This is a seeming effect, and it is akin to the phenomenon when you look through a crystal at some text. Clear that in some places the letters are larger, in other places they are smaller. And if you move this crystal along the text, the sizes and the directions of motions of these letters change. This is an approximate explanation of the seeming motion of quasars in Pavlov geometry. This is not real, but geometrical effect. And in fact, the quasars may move more chaotically or even be at a stop. But to the observer, they will seem to be not simply subject to some Brownian motion, but tending to some fixed directions. However, we live not in space, but in space-time. Besides, it is not only space that can be curved, but also time. It follows that not only the ordered motion of quasars is an illusion, but their abnormally large luminosity as well. We can also exclude the hypothesis that during only 1 minute we perceive the light emitted by a quasar during an hour or even more. The second effect for which we could check the prediction of geometry with Pavlov metric is the anisotropy in the relic radiation temperature distribution. If we use Minkowski geometry and consider the observer who moves in an environment of relic photons, then, if he moves relative to the relic background, the photons that fall on him from the front have larger temperature. The photons that he registers from the back side have lower temperature. This effect is well known. It is called the effect of a kinematic dipole for Doppler effect in Minkowski space, and is available for observation. If we look at this more carefully and fix the changes of temperatures due to such Doppler effect in Finsler geometry, and be able to register 10 in -5th or -6th kelvins, then in Finsler geometry alongside with dipole there will be quadrupole and octupole that will also have kinematical character. And it is not hard to find out if it is kinematics that defines the quadrupole and octupole anisotropy, or it is connected to the universe evolution after Big Bang. If it turns out that quadrupole and octupole anisotropies in the observable picture of CMB have kinematic origin, the physicists will have to accept Finsler geometry as the basis of the spacetime model. The presence of a dipole can be easily explained within the limits of the habitual relativity theory by the motion of our solar system relative to the field of relic radiation with a speed of about 400 km per second. As to the parameters of quadrupole and octupole that are already found in the distribution of relic radiation, they make the astrophysicists stumble. The dipole in Doppler effect has an axis parallel to the axis of the observer's motion relative to relic background. It is a solid fact. If we consider the same effect in the space with Berwald-Moore metric, then not only dipole axis will be parallel to the observer's motion, but those of quadrupole and octupole as well. It is just this parallelism, or close to it, valid for all the four axes that we observe in the picture of relic radiation detected by the American satellite MAP. It is this coincidence of axes of a dipole, quadrupole and octupole that has been given the loud name of a world axis of evil. It has no explanation in frames of modern model of the universe, and in Finsler geometry it is a simple consequence of Berwald-Moore metric usage. Already now we can carry out a simple experiment with the help of which it would be possible to tell whether the presence of quadrupole and octupole anisotropy in the distribution of relic radiation is due only to our three-dimensional motion in space with Finsler geometry, that is a consequence of pure kinematics, or we should search for its reason in the deep past of the universe. Our planet rotates around the Sun with an average speed of 30 km per second, meaning 30 km per second in one direction and 30 km per second in the opposite direction once in a half a year, that is half of a turn around the Sun. This gives the difference of about 60 km per second. And this is already a noticeable value in comparison with the average speed of solar system motion relative to the field of relic radiation, which is equal to 400 km per second. 60 km per second is a sufficient value of difference in speeds at different moments of time, enough to register that if the axes of dipole, quadrupole and octupole are kinematical, they will turn for about 10 to 15 degrees. If these 10 to 15 degrees for all three multipoles vary together, then it is kinematics. If it is only the dipole that turns, as it is supposed by the modern view on Doppler effect connected with the relic radiation, then there is no reason to change the Minkowski metric for Berwald-Moore metric, because quadrupole and octupole will appear to be not kinematical. To confirm or disprove such a prediction, we don't need too much. It is enough to compare two pictures of the dipole, quadrupole and octupole anisotropy and the distribution of relic radiation taken in an interval of half a year. These two pictures can shut down the question of a kinematical or non-kinematical origin of the lowest multipoles. As far as I know, in the near future, Planck mission is planned to start in frames of the European space program. It would be extremely interesting if the satellite performed such measurements and give an answer to this question. The problems facing mathematicians and physicists have fundamental character. They can be hardly solved individually. Here we need the efforts not only of a group of researchers, but of a whole scientific collective. In 2003, on our conference on Einstein theory of relativity, Dmitry Pavlov gave his report for the first time. It was proclaimed that Finsler geometry can become the basis of the new theory of spacetime. From this moment, the energetic development began, not only in research, but also in the organization of it. Since then, the collective of scientists that has now formed the staff of the Research Institute for Hypercomplex Systems has organized 5 international conferences, 3 summer schools for young scientists and postgraduate students with extensive lecture courses on the foundation of Finsler geometry. It has published 2 monographs and a considerable number of papers in the prestigious editions. The results show that the activity in this field is very high. From the point of view of geography of participants and representatives of leading scientific schools in this field, our conferences are indicative. Europe, Asia and America are present. It took only several years to collect the leading schools under the aegis of our conferences. This conference brings together up to 70 scientists from the different countries of the world. Sometimes there are up to 20 countries represented. Among them are those that have an outstanding place in Finsler geometry studies. These are the USA, Romania, Hungary, Russia and China. Every time we choose where to carry out this meeting, taking into consideration that the majority of the scientists are Russian citizens, we sometimes have it in Russia. But every 2 years we go to Egypt to get closer to pyramids of Egypt that have the pattern which reminds those discrete symmetries found in Berwold-Moore matrix. If we take a 4-dimensional hypercube and look not along its main axis, but move from the top into its center and make a section orthogonal to its axis to get a 3-dimensional hyperplane, we will get an octahedron. Half of this octahedron gives almost exact copy of the Great Pyramid on the Giza Plateau. Similar symmetries can be found in a rhombic dodecahedron. If we connect only those vortices where the 4 faces converge, we'll get the octahedron that can be got if we connect 2 of Great Pyramids by their bases. This figure, rhombic dodecahedron, has a lot of discrete symmetries. Some of them coincide with discrete symmetries of an octahedron. And if we cut an octahedron into halves, there appears a pyramid. Add another one, here is an octahedron. But the octahedron is not convenient for research. If we want to investigate discrete symmetry of spacetime by means of such figures, it is more convenient to take half of the octahedron, just this pyramid. 2 other pyramids on Giza Plateau have just a bit different angles of the side slopes. The same angle is at the bottom part of the broken pyramid in Dashur. The upper part of this pyramid has another slope angle, close to 45 degrees, almost the same as the angle of the faces of Red Pyramid, which is located in the neighborhood. Again, strange coincidence. Have a look at the vortex in which 4 edges meet. If we cut off such a vortex, we get a pyramid again. But not as the one, which is a half of octahedron, but that with a slope angle of 45 degrees, that is more flat. Aren't there too many coincidences? By the way, the pyramids of Giza and Dashur essentially differ from all the other pyramids of Egypt by their level of construction. Moreover, the level of technologies in stone processing and building techniques that were used when these pyramids were built surpasses even the level of some modern technologies. All of this points at the hypothesis that the civilization which was able to build such constructions could possibly surpass us in scientific knowledge as well. Building of the pyramids with the parameters of rhombic dodecahedron indirectly specifies that the builders were probably familiar with the Finsler geometry. And not only familiar. Observing the surprising facts that concern Egyptian pyramids, one could sometimes think that these pyramids could be intended not for the ritual purposes, as it is accepted now in the Egyptology, but could be some devices or parts of installations for checking the Finsler nature of space. However low the probability of such hypothesis is, it is not zero. And it seems it is possible to check if such strange hypothesis could be real. We can't exclude that they were special antennas to receive the signals or to investigate the objects on the borders of our universe. And the choice of the pyramidal form instead of habitual parabolic antennas is caused by Finsler properties of our space. In Riemannian geometry, the focusing surfaces, lens surfaces or reflecting surfaces, have the form following from the expression for the metric of the quasi-Riemannian space, Minkowski space. That is, they are paraboloids or parts of spheres. All these are the surfaces related to the second-order equations for the metric. If we want to register something coming from the faraway source of radiation with regard to Finsler geometry, it could be possible to use some specific form of prisms, pyramids, parts of rhombic dodecahedron and so forth. No doubt, such ideas will seem heretical to historians. Quite probably not only to historians, and not only about the Egyptian pyramids, but also the other ideas which were discussed earlier. The modern physics considers geometry to lie in the foundation of physics, and algebra is something already secondary. Surely this idea sounds heretical from the point of view of modern physics, but as any heretical idea, it has a chance to realize. Because the heretical idea is an idea uncovering some deep moments. So there is a chance that behind this idea there is something that could help us to look at the world from an unexpected side. And as I already said, in modern physics the most important deficiency is the deficiency of deep ideas. Therefore, in the current state of affairs, the strange ideas are good. It is impossible to stop the flight of thought. Nobody can forbid me to build the imaginary worlds. At the same time, if they are equipped with beautiful mathematics, and if they give quite concrete predictions of observable effects, then I can construct an a priori theory to express my intuition and try to compare it to the experimental data. The very idea of Hamilton that algebra is the basis of geometry and hence is the basis of physics doesn't mean that we know this algebra already. If Hamiltonian's dream is true, then at some moment we will say, here is this algebra. But we don't know this algebra yet. It could also be that it doesn't exist. Hamilton's dream could be a utopia. But if it is not a utopia, then at some moment our eyes open and we say, wow, we understand how the world works.